Ladies and gentlemen, welcome back to Engineering Dynamics. In this video, we will be talking about relative and absolute accelerations in different coordinate frames. So let's jump right in. We are given this beautiful example. And what we are interested in is the acceleration of the ball in coordinate system t and the acceleration of the ball in coordinate system r. So we have three coordinate systems. The first is, of course, our initial coordinate system. That's x, y, and z. And then we have our rotated coordinate system. That's t. So we have x and y. That's rotated with a constant angle alpha. So it's tilted and it's not turning. And then we have our rotation around theta around the coordinate system r that we have here and xr that we have there. So we have three coordinate system I, t, and r. And the first one is, but we want to find out how do we get from I to r, so the rotation. We do that by looking at it from the top. So this is basically a top-down view. We first take the unit vector in I, that is this one, and see how it is described in the coordinate system r. So we have here the angle. In our case, it is theta. So we get a cosine in x and a sine in z. We turn around y, so it's xy. So we turn around y, nothing is happening in y, that's why there is a 1. And then we take the unit vector z, it's that one. We go minus sine in x, and we go cosine in z, so that's here, and we go minus sine in this direction. So that's how we get minus sine and cosine. We do the same for the transformation matrix from r to t. We do the same thing. We get the unit vector in x, show how it is described in t. We get the unit vector in r and see how it is described in t. And we do the same thing for z, but the z-axis is the axis that we're turning around. So we're x, y, and we turned like this. So this is why z is 1. So it's 1, 1, 0. Then we want to know, of course, the accelerations. To get the accelerations, we have to first see that this is not an inertial frame. So R and T are not our inertial frames that we described here. And that's why we can't just use a time derivative. We have a specific rule that we have to follow. First of all, we have to derive our acceleration, our velocity in t, then add a rotation parameter. So this is because of the rotation. This is our speed or our velocity, and this is our rotation that our point is experiencing in coordinate system t. To get the velocity that we need to derive, we of course need just the derivative of our point B in coordinate system t, and then again to get the velocity, we know that we have a rotation component that we get by omega cross r. So if we have a point, the point can accelerate in this direction because we don't have a rigid link. So we have a point here that can move in this direction, but then it also has this rotation component that we have to remember. And we know, of course, the position of our point B and T because that is given with x. So it's just S0, 0. To get the rotation of our coordinate system, of rotation in t, we have, of course, the rotation around omega dot in r, and we have to transform it from r to t. So we use the transformation matrix where we turned around, in this case it was alpha, that was a constant, times our angular velocity, and we get our rotation speed in the coordinate system t. Then we derive it once, so this is just s dot. Then we do the cross product. The cross product, of course, is a lengthy operation, but you just have to do it. It's this one times this one plus this one times that one. The same for the second component, this one times this one minus this one times that one. The third component is this one times this one minus this one times that one. And that's how we get a third component. So summing all up, this one and this one, we get our velocity of point B in t. Then, of course, we have to derive it once with time, but we can't forget our rotation. So now we have to do, again, the cross product, but now with the velocity. So we go from here to there, from here to here, from here to here, from here to there, from here to here, and from here to there. And that's how we get this lengthy expression. Now we have to add this one, and we get the acceleration of body B, so our ball, in coordinate system t. And we can express that acceleration in, first of all, the relative acceleration, the centripetal acceleration, the Coriolis acceleration, because our point is moving and thus experiencing acceleration, and the peripheral acceleration. And if we now want to transform to get the acceleration of point B in body R, we can just use the acceleration that we already know and transform it from t to r. We don't know the transformation matrix from t to r. We only know from r to t. But we know that if we invert our matrix, we can go the different way. So we invert it, and now we can go from t to r. But inverting is always difficult. The other important fact, or let's say ability of transformation matrices, is that inverting and transposing is the same. So instead of inverting, we just do a transposed, and now we can express the velocity of our point B in coordinate system R just like we wanted to. So this is just a simple operation that we can do, and we don't have to do the whole derivation from top to bottom again. I hope this video gave you a small introduction on how we are working with transformation matrices and how we can get velocities and speeds in different coordinate frames if we just have the right transformation matrices. Thank you very much for your attention. If you don't have any questions, if you have any questions, you can put them down in the comments, and I'll see you next time.